Calculate the pH of a 1.05 molar solution of NaOCl. The Ka for HOCl is 2.9 times 10 to the negative 8. So before we can sort of solve this problem, we're going to have to establish what NaOCl represents. Is it basic, neutral, or is it acidic, right? So let's write this down. NaOCl. Let's decompose this into its ions, right? Na and OCl. So starting off with Na, right? Well, we know NaOH exists, and it's a strong base because of the hydroxide. So Na, being the conjugate of a strong base, means that it's going to be pH neutral. So Na is pH neutral. Now what about OCl? So we're given in the problem that we're given a Ka for HOCl. So just by that, we know that HOCl has to be an acid. So HOCl is acidic, and since it doesn't, it's not listed in the list of strong acids, then that means that it has to be a weak acid. So this is going to be weak, right? So we know it's a weak acid, and we know this ion is OCl. So the conjugate of a weak acid is going to be basic, right? That means that OCl is going to be basic. So with that, we now know that Na is going to be neutral and OCl is going to be basic, which means this solution has to be basic, right? Because a neutral and a basic yields a basic solution. So let's write a base dissociation. NaOCl plus H2O is going to give hydroxide plus NaOClH plus, right? So let's make an ice table, and we're starting off with 1.05 molar. This doesn't matter, and we're not given any initial concentration for hydroxide or this. So this is going to reduce by minus x. This is going to gain x. 1.05 minus x, right? This is going to equal to x squared, 1.05 minus x. Now what are we going to put here, right? Well, we cannot put the Ka because this is a base dissociation. We're going to have to use Kb. So how do we get a Kb, right? So we get a Kb by knowing that Kw is equal to Ka times Kb. So if Kw is equal to 10 times 10 to the negative 14, right? Then that means that we could just do 10 to the negative 14 and divide it by 2.9 times 10 to the negative 8. So that's going to give us that will give us 3.45 times 10 to the negative 7. So now we're not going to use the quadratic formula to solve this. We're just going to assume x is small. So we're just going to do, we're going to solve it. So if we assume x is small, right, we're going to ignore that this exists. So then we're just going to solve this as it is. So this would just be the square root of 3.45 times 10 to the negative 7 times 1.05. That's going to equal to x. So that's going to give us x is equal to 6.02 times 10 to the negative 4. I should fix this up a bit. 10 to the negative, sorry about that, 10 to the negative 4. So to confirm this, we'll use the 5% rule, right? So if we do this and divide it by 1.05, and then multiply it by 100, we get a percentage of 0.057. That is way below 5%. So we can assume this. So we can assume this. We can assume that x is small, and that this is going to be our x value. So if x is 6.02 times 10 to the negative 4, that means that our hydroxide concentration is going to be 6.02 times 10 to the negative 4. So now let's find the pOH, right? Which is negative log of 6.02 times 10 to the negative 4, which is going to equal 3.22, right? Since that's our pOH concentration, we're going to need to use this number, subtract it from 14. So 14 minus 3.22 is equal to 10.78. So that means that pH is equal to 10.78.